Hello everyone, my name is Hossein Resani and I'm going to present our paper titled Continual Learning in 3D Point Clouds, Employing Spectral Techniques for Exemplar Selection. Okay, let's see what the problem is. In traditional machine learning, a model trains on a fixed dataset and remains static, unable to learn from new data. Continual learning solves this by updating the model with new data while it retains past knowledge. This allows the model to adapt and improve performance in dynamic and real-world scenarios. Continual learning is quite challenging because the model must avoid catastrophic forgetting, which basically means the loss of previously learned knowledge when updating with new data. The solution is pretty simple. We want to save a small set of samples, let's call exemplars, from previous classes to help the model remember. The challenging part is picking the most useful samples because memory is limited. That's where our work comes in. We use clustering to make smarter choices for selecting exemplars. So why do we use clustering? Here we're showing some feature embeddings from the ModelNet 4D dataset. As you can see, the feature space in the point cloud domain is not unimodal. As you can see, it actually forms distinct clusters. This probably happens because unlike the image domain, we don't have large datasets with thousands of samples, or let's say super strong backbones to rely on. So in this situation, we want to use clustering to select the most representative samples for each class. When it comes to exemplar selection, there are a few options. You can pick samples randomly, but actually it doesn't work well. Another approach is herding, which picks samples closest to the class centroids. It's popular in 2D continual learning, but in the point cloud domain, it performs poorly because it often selects very similar objects. As you can see on the right side, our model successfully selects different samples within the airplane class via clustering. Okay, let's dive into our approach. Here, what we're going to do is applying spectral clustering across three different domains. I mean, the input space, the local feature space, and the global feature space. We explore the effectiveness of each domain individually and also different combinations of them. And finally, by fusing all three domains, we achieve the best performance and outperform all individual and combined approaches. Before we continue, you might ask, why spectral clustering? It's because of the non-Euclidean nature of raw point cloud data, which basically means you cannot add or, for example, average without preprocessing. So spectral clustering solves this by embedding the data into a new space, then apply clustering. This makes it the best choice for this type of data. Let's get back to our approach. To apply spectral clustering, we first calculate a similarity matrix based on distances between samples. And for input and local feature space, we use the chamfer distance, which commonly used in point cloud domain. And for the global feature space, we use the Euclidean distance. We apply spectral clustering in all three domains and extract spectral embeddings and combine them into a unified representation. Then we cluster this fused representation and select diverse samples near the cluster centroids. These exemplars are stored in memory for the next incremental stages and help the model to retain knowledge effectively. Now, let's talk about another big challenge in continual learning, the class imbalance problem. This happens because as the model moves to new learning stages, we can only store a small number of exemplars from previous classes. Meanwhile, we have a much larger amount of samples from the new classes. So as a result, the training data becomes imbalanced and leading to the model overfitting to the new classes and forgetting older ones. So, what's the solution? To address the class imbalance problem, we replaced the standard cross-entropy loss with focal loss. Focal loss works by focusing more and more on the old class exemplars and less on the new samples. This helps balance their contributions during training and prevents the model from overfitting to the new classes. Here are the results of applying spectral clustering in our model. As you can see, our model effectively groups similar subtypes together. We also conducted our experiments on 3 datasets, ModelNet 4D, ShapeNet, and ScanNet. Here we're showing the results on ModelNet. And as you can see, our model outperforms other methods. And it's important to note that the joint approach, I mean green dashed line, represents the upper bound, where the model is trained on all data at once. And the forgetting approach, red dashed line, is the lower bound, where we don't have any solution for catastrophic forgetting. This slide shows the memory usage across incremental stages on the ModelNet dataset. And our method uses only 50% of the memory compared to others. This highlights that our model is not only effective in performance, but also highly memory efficient, which makes it a much more practical solution for real-world scenarios. On ShapeNet, our model maintains high accuracy and reduces memory usage by 47%. Even in the real-world dataset, I mean ScanNet, our model performs best and reduces memory usage significantly by around 72%. For the ablation study, we show the effectiveness of focal loss compared to cross-entropy loss. As you can see, the plot shows the advantage of focal loss in handling class imbalance. In another ablation study, we're going to explore different combinations of input, local, and global features. The results show that combining all 3 features gives the best performance. To wrap up, we introduce CL3D, a novel exemplar selection strategy for continual learning in point clouds that uses spectral clustering. Our method achieves high accuracy and reduces memory usage, which makes it efficient and practical. Thanks for your attention.